Okay, let's begin. Thank you everyone for coming to our talk on machine learning and how to hack it. I'm going to begin in a moment, start with a short introduction and walk you through the stuff. I hope you'd have a fun time. This was a very fun talk to construct, and I hope that we'll be able to share the fun that we've had doing it. So first and foremost, I would like to acknowledge our employer and give you a chance to go over the legal disclaimer and to understand all of the terms and conditions that apply to this talk. Thank you. No, seriously, I really do want to thank our employer that actually allows us and helps us to do these things. I am required by legal to show you this slide. I'm not required to make you read it. We haven't harmed any machine learning systems, horses, penguins, flamingos, etc., as you would see throughout the talk. And a bit of introduction about ourselves. My name is Barnhart Magen. This is Ezra Caltum. We are both founding members in B-Sides Tel Aviv. Ezra is running the local DEF CON group in Israel, and we are working together for almost a year now. This talk has been built on a lot of information and a lot of research that has been shared with the community. And I want to acknowledge that because a lot of time when people come and present their work on stage, it seems like they've done everything themselves. Nobody does it themselves. Nobody's working alone. Nobody's doing everything from scratch. And we should acknowledge that. And to help you to see where we learn stuff and where we got that information from, you can usually see a link at the bottom right corner. You don't have to take pictures of that link. We will release the slides when we finish our talk, but just so you will have like a reference point to know where things are coming from. You can always take pictures of me. And I also wanted to acknowledge a very important thing, and we wouldn't be here today without it, and that is Shears, which is Ezra's fiance. Ezra is getting married in 10 days, so the fact is actually right here, right now.
So, as you can imagine, I'm doubly terrified. First, because I'm delivering a talk here. Second, because she wants to kill me because I'm here and not organizing the tables.
And a bit of background, how did all of that begin? So last year, at DEF CON 25, we sat around some sofa as a group of friends and we started discussing what AI is, what machine learning is, how does it apply to our everyday life as security researchers, how difficult would it be to actually break machine learning systems? And that discussion got us going and we opened like a new research venue for us and saying, okay, let's see what we can break, let's see what we can do with that. And that was last year, and we're here this year just to present the results from our research. So we're going to talk a bit about what machine learning is, what kind of attacks can you do on machine learning system, what works better, what doesn't work at all, and where you should focus your attention both as an attacker, defender, and a researcher. Whenever there's something that I want you to pay more attention to, I highlight it in yellow. And we're not going to talk about like 0 days in machine learning and what do they mean. You can catch us after the talk and to explore that a bit more. But I do want to give you like a breadth of information about what those systems are, what they are not, what you can do about it. So I want to kick this off with a story about a horse. This is a very clever horse called Hans, Clever Hans, 1903, Austria. And the reason he was named Clever Hans was because he could do stuff that other horses couldn't. For example, he could solve simple arithmetic question like 2 + 3, 1 + 5, stuff like that. He could spell words in German, which is amazing for any horse, and also because it was in German. And a psychologist was tasked with understanding how was that horse so clever. And in a general scale, it's pretty clever to be able to do those things. And that psychologist came to what we call now a double-blind test. And what he found out was that the horse was actually very, very clever. And the reason he was very clever, not because he knew how to do arithmetics or spell words in German, but because he would read body language cues out of his handler, which you can see here. And whenever his handler would say, how much is 2 + 3? And he would tap his hoof on the ground, 1, 2, 3, 4, 5. And then he would detect that the handler knew that he got the right answer, and he would stop. So he was a pretty clever horse. And the reason I'm telling you this right now is because in many aspects, machine learning today is very much like that horse. Machine learning today is very good at solving specific well-defined problems. Whenever you're trying to go outside of the scope of the well-defined problem or to try to cross domain from one knowledge domain to a different knowledge domain, everything breaks. And it usually breaks horribly. And we'll explore that in a bit. So some background, some common language to help us understand what we're talking about. The first thing is, whenever people are talking about machine learning, I want to make it very clear what do they mean. Machine learning is a system where you push in lots of inputs and usually apply some metadata to those inputs, and the system has a way to recognize what those inputs mean according to those outputs and to get that information out. And then it provides some labels. So if I provide it with image of a cat and a label, this image is a cat, and a different image with a dog and a label that says this is a dog, the next time it will see a cat without any label, it will be able to properly apply the label cat to that image. So the trick behind machine learning is how to teach the system ingesting so much data and coming out with the correct answers at the other end. Deep learning is the same thing without any metadata. And that means I take a lot of images. In our case, to train a system to recognize cats and dogs would take like maybe 1,000 images. Creating a deep learning system would take 1 million images, 10 million images. So we're talking about orders of magnitude more data, but without any kind of metadata attached to it, which is very relevant in a lot of use cases where we don't have the metadata or it's too costly to create that metadata. But then we have artificial intelligence. Artificial intelligence is something else completely. Usually when we're talking about artificial intelligence, we're thinking something like Terminator or one of the very nice robots in any kind of science fiction television show. But the reality is that artificial intelligence is about context. It's about understanding more than what you're actually seeing. When you're looking at that picture, there's something more to that picture than an image of a girl or a flamingo or a hedgehog. You look at it and say, okay, I know that picture. This is from Alice. This is Alice. She's about to play cricket. She knows what she's about to do. She's hugging the flamingo. She's going to aim it, whatever. You have a lot of context. That context allows you, as an artificial intelligent impersonation, to know more about what this is about this image and what is the general context that it fits. AI systems today are nowhere close into doing this. Nowhere. We are talking not like 2 years away. We're talking of 50 years away. We are nowhere near artificial intelligence, which is why whenever anybody's talking about AI, they're wrong. They're talking about machine learning. And whenever I say AI, I'm wrong, and I apologize. I actually mean machine learning. So that's like a big misnomer in the industry, and everybody should pay attention to it. So what do I mean when I am saying that AI systems are created to solve very well specific problems? Specific problems might be like, how do I detect an object in that image? How would I detect a payload in that net flow? How would I detect if this specific binary is malicious or not? So these are very well-defined problems to an extent. But if I'm saying like, how do I detect this language and I know what the words are and I also transliterate it into something else, this is like a stack of algorithms, not a single algorithm. And the reason that this is built in such a way is because there is no single algorithm to rule them all. So you have to build your system out of a lot of different components, different algorithms for different purposes. So let's talk a bit about machine learning. Machine learning, and in my example here, I'm using neural networks. There are other methods as well. Usually describe a network or a graph that has weights and has nodes. And when I'm talking about that pieces of information, this is the mathematical representation of it. Usually, we are not very much concerned with the mathematical representation of it unless we're data scientists. If we're not data scientists and we actually want to use those systems, we're talking about code, we're talking about data, we're talking about how to parse specific inputs into whatever the system is expecting to ingest. So it doesn't matter if we have a small network or a large network, and by the way, small and large here means that a small network could be a couple of megabytes, tens of megabytes in size. Deep learning networks can go up to tens and maybe 20 gigabytes in size. So there's a big discrepancy between small networks and large networks. A large deep learning network would have on the order of magnitude of something like 100 million different parameters. So that's very all interesting if you're into how to build those systems. If you're into how to deploy them, it doesn't matter as much. So what are the concepts that I want you to recognize to help? The first one is that there's a concept called topology or layout, and this is the way that the network is constructed. Does it have a lot of nodes, a little nodes? How are the nodes interconnected between them? Do you have a lot of connection, only a few connection? How are those connections defined? What kind of mathematical property do they have for each connection? What function defines them, etc. The actual parameters themselves, the numbers, they actually have meaning. So those numbers, we also call them weights or parameters. But the bottom line, the most important aspect of it, whenever we're discussing machine learning, the real IP, the intellectual property behind all of this is the construction of that network, not the way that you defined in order to construct a network. But once the network is built, that's your IP. This is the thing that you want to protect. Once you deploy it into the field and somebody gets a hold on your IP, that's it. It doesn't matter how much you invested to build that IP. Once it's there, it's there. So what happens when we go about it from a mathematical point of view? If the mic is just speak loud, okay, it keeps cutting out. From a mathematical perspective, what happens is that we are representing those models with matrices. So we have one matrix to represent the weights and the parameters, and we have a different matrix to represent the edges of that graph or the coefficients, and we multiply all of those matrices together, along with a matrix that represents the input. The bottom line is that whenever you're multiplying matrices together, you get another matrix. And that's all good and fun, but we don't really care about the math. We just care about the code. How does it look? So when we're looking at it, we're looking at vectors, which are arrays, or we're looking at two-dimensional matrices, which are arrays in memory. So the bottom line for all of that math speak is that it doesn't matter how the data scientists build the system. The bottom line is that if you have a blob in memory that represents all the data, if you're able to fill that data, you're just speak normally. Yes. It's a different domain for each of them. And whenever the system ingests that information, does its black voodoo magic stuff, in the end, you will get a prediction. For example, if you feed it an image of the cat as an input, you will get a prediction, which is a piece of string that's an output from the system that says cat with 0.78 probability of confidence. But I want to disambiguify this information. So this is not black magic. This is not voodoo. In the end, what happens is that you have a very short stage called intermediate representation, where you take the input, might be an MP3, might be an image, might be a binary, and you convert it into something that you can multiply the matrices with. In other words, you encode that same information into a matrix with whatever method that you decided to do. It's very important which method, but it's just a way to encode that information. Then you multiply the matrices. There's lots of very smart algorithms how to do this efficiently. Nobody cares. You just use the library. And then you get the outputs. The outputs are very interesting because whenever you're feeding an information into those systems, usually you don't get a single output. You will get a vector that describes what's a different probability that it matches one of the classes that you have in your data. So if I put an image of a cat into the system, it will say, well, it's a cat, 0.78% probability, but it also might be an airplane, 0.01 probability. Okay, so all of that information is being outputted by the system. But the way that the system outputs that information is not by using a lot of strings, it's just using indexes. So it doesn't say cat 0.78, it says index 17 0.78. And then there's a mapping process where you map the results into something that's human readable or human identifiable. And then you get the prediction and your system is working and everybody's very happy. So when you're training the system, it's a very iterative process. You take that information, the first image of a cat, you feed it into the system, you measure the accuracy, feedback loop, take the second image, calculate whatever you got back, measure the accuracy, correct the weights, correct the parameters, repeat this 15 million times, okay? I'm just throwing a number, it's usually much higher than that, might be 500 million times. And this is where most of the compute is going when you're creating the IP, when you're creating the model. When you're deploying the model, something else completely. It's almost like a deterministic, almost linear process. You don't retrain it, you don't modify it, you don't change it. You actually have no integrity to know if someone changed it, but we'll come back to that later. And what you have here is just the same method going from end to end, feeding information on one end, getting results on the other. However, looking at models and looking at code is not the same thing. It's not the same thing because whenever we're looking at code, we can look and discern the execution flow. We can open it in IDA, we can look at the disassembly and say, okay, this is what they meant. This is the code that generated this assembly. I know what it means. But when I'm looking at the machine learning model, well, I have a bunch of math operation and a matrix. What does that mean? How do I know what it encodes? And the short answer is that you don't. The longer answer is that those same data structures that we're familiar with from the structures in memory and the way different data is represented in the code, in the data segment, the code segment, etc., it's not transferable into the same kind of structures when you're looking at matrices. So there's a big open problem today saying, how do I reverse engineer a model to know how it became that model? What were the set of circumstances that created that model? And again, more on that later. The crux of the matter is you can't do code review to a matrix. You can't really do reverse engineering to a matrix. And how would you even know somebody did something fishy to that model? And we're going to show a couple of examples. The first thing that I want you to know and to really get from this talk, machine learning models aren't scary. In the end, it's just pieces of code floating somewhere in memory. So what you're seeing here is actually a machine learning model called Resident 50 because it classifies 50 different objects. And this is just a hash dump. This is just a piece of memory. There are no transfer functions here. There is no nodes, graphs, etc. This is the way it's represented in memory, and this is the only thing that we care about when we go about it. So, three different important things to mention. The first one is that those algorithms, the ones that are training the systems, are optimized to detect the strongest signal in the input. It might not be the input or the signal that you would expect when looking at that input. The machine learning model might look at a picture of a cat and decide that this is a cat not because it has some whiskers and eyes and pointy ears. It might decide because this specific pixel relationship and the histogram in that image signifies that this is a cat more than anything else. So it's not analyzing the input the same way that we are, but it's getting to the same result. The optimization is built in order to fixate on the strongest signal in the image. And if we have control of the strongest signal in that input, we can do nifty stuff. The other thing is that these are very, very large pieces of memory. This is not like disassembly and 4 megabyte binary. This is 6 gigabytes in memory and growing. So it might be somewhat problematic to reverse engineer whatever you have in memory. You need better tooling and better perspectives. And the last thing that I want to discuss is the bias. So I want to tell you a short story. So some researchers tried to build a machine learning system, a machine learning model, taking various blood type information, mean corpuscular volume, number of red blood cells, etc., in order to detect cancer. So they took a lot of inputs, some of them from cancer patients, some were not from cancer patients, but a lot of data, like a very large CSV, comma-separated value file. And they went over all of that information and they built the machine learning model, and they were very happy because they created a system that had 97, I'm just making up the number right now, 97 plus accuracy of detecting a cancer patient based on his blood type, parameters. But whenever they tried to use this in the real world, it failed horribly, gave very, very low detection rates. And they tried to debug their system and to understand what went so horribly wrong. And what they discovered is something that is usually related to something we call bias. And that means that the data that they had, the strongest signal in the data that they had was the name of the hospital. So if you went to Sheffield General, it doesn't mean much. But if you go to John Hopkins Center for Cancer Research, it's a good indication that this patient has cancer. So when I'm saying that somebody is fixating on the strongest signal in the information that you're providing it, this is one of those examples. And they had to scratch the entire system and rebuild it completely. These systems have a lot of different attack vectors, and I'm describing just a couple of those attack vectors here. And we will be discussing those highlighted in red today. We will talk a bit about how backdoors, denial of service, IP theft, mispredictions, and model tampering look like in those systems. But specifically, there are a lot more different attack surfaces, and we'll be happy to discuss them more offline, off stage. We wanted to use a common framework to discuss these different threat vectors, and CVSS seemed like a very natural subject to do so. So we took our top five attack vectors denial of service, misprediction, model tampering, IP theft, and vectors, and applied CVSS scoring to them. And we rank them according to their CVSS score. As you can see, DOS is the most important one here. And then we went to talk to our various customers and partners and asked them, well, what do you care most about when you're deploying AI systems? Well, they couldn't care less about DOS. They didn't care at all about misprediction. The most important aspect to the way that they were looking at it from a business impact point of view is what would happen if someone steals my IP? What would happen? How do I protect myself against those kind of things? And if I'm running that IP somewhere, if I'm running that machine learning engine somewhere, how do I know nobody changed it, nobody tampered with it? Is it even doing the same thing that I expect it to do? Because I have no controls, I have no metrics to measure. Is it still doing what I'm expecting it to do? And in the end, we wanted to answer some very simple questions. How would an attacker actually attack these kinds of machine learning systems? Assume that there is a machine learning system doing something somewhere, usually involving the cloud or blockchain, whatever buzzwords you hear. And how would an attacker go about and attack these systems to either steal something, get something, gain something, escalate something, whatever something? So in order to discuss this, I'm going to hand the mic over to Ezra.
Thank you, Guy. So first I'm going to try with this one. It seems to work. Cool. So we had now to build an attack, and we could go to two different parts of it. First, we could try and go against our systems, or we can try and go through the algorithms. And to be able to explain that, let's do a little recap. So if you remember, the first phase on our process is we got an input, and this input is a file, or it's a MP3 file, or a bitmap, or whatever. The system doesn't understand bitmaps. It needs to convert it into a matrix or internal representation. So there is a parsing process in here. This is a fully systematic operation and less of a mathematical one. And then we have the parts that the algorithm itself, it's working and it's performing the magic inside. And afterwards, it's mapping the output from this phase, from the algorithmical phase, into an index. Again, imagine this index as also something systematic where we have a number and a label to that number. Okay? So we wanted to attack both the scenarios, and we're going to start with the system part. And I just want to return to the first part and want to understand something. If you remember, we have an image that needs to be converted into a matrix. That's parsing. That's something that it's very known in the industry, and it's a simple parsing because machine learning needs to convert whatever you shoot at it into matrices. And parsing is hard. I mean, it's hard. And whenever there is parsing involved, there is fun to be had. Oh, and most important, whoever develops AI or machine learning, do not develop file formats or parsers or whatever. It's not their specialty. Their specialty is matrices and data. And you know what usually happens when you don't know how to do a specific file format? You just bring a dependency. Cool, they are bringing outside libraries to the project and to their stack, and these outside libraries need to perform in a very specific way that gives very specific parameters, because the entire model is trained on those parameters, and if the parameters change, the model changes. So we bring now supply chain, we bring now patch management, which traditionally is hard, but when you have changing parameters, it's harder. And it's harder in the really bad way. Oh, and yes, you cannot support a single format. Because imagine that you are now creating a framework that does image recognition and can only support a single format. It wouldn't work for anything because it's just one format. So you support many of them. The obvious thing, what we wanted to do at this moment was to try to fuzz the file format parsing. And we failed. And we didn't fail because it was JARVIS. We failed because we had, for example, a huge cluster. And this cluster was running all the time these machine learning predictions. And that means that the entire machine learning process was being run. So we failed. We didn't take into consideration that machine learning is an operation-intensive process. And we were having terrible results, and we were not having anything. So we decided to start and take a look at what could be happening there. So we were focusing on fuzzing a common framework that it's called CAFE. And our approach when we were fuzzing it, it's having full coverage, because when we're fuzzing CAFE, we're fuzzing the actual target, the actual objective, and we find something there is going to be the same thing that it's going to be on production or whatever. But it was slow. And I want to be clear here, in case I was not clear enough, we were, in every iteration, we were running a machine learning prediction.
Just to tie it a bit to numbers, is that we ran the entire machine learning end-to-end single prediction in around 200 to 300 milliseconds, where you would get 2 to 3 different iterations per second for fuzzers. This was 3 orders of magnitude too slow to actually produce viable results. So we needed a system that would do this at 2,000 iterations per second. And we were very, very far away from that.
So you know what happens whenever we have a challenge like this? We get to the next level. So basically, CAFE is using a framework that it's called OpenCV, Open Computer Vision, where, yeah, it was also used to parse the images. However, it has a problem. It has limited coverage. We don't know, we're not using all the code paths that are in there. And it could be that something that we find it's not relevant for the exploitation that we want to attack, because it's simply, there is no code path in there. But the speed was acceptable. And we are going to return to this in a few. On the other hand, we could have gone directly to fuzz the specific libraries that are being used to parse the file formats, like going to libbmp or libtiff or whatever, which would be extremely fast. But if in OpenCV we have limited coverage and we didn't know if the code paths were being taken, over here, it would be extremely more complex, because it could be that the model are using very specific functions. The framework is using very specific functions. So at the end, we choose OpenCV. It was the best trade around between speed and code paths and whatever. However, we also found something very interesting. Upstream. Fuzzing is not needed sometimes, because as I was explaining before, the fact that there is some modification in the parameters that are being fed to the model could extremely affect. Or further, and true story, it can actually be using libraries that are not even supported anymore. I'm not going to name names, but you can definitely go and take a look at the source and you will immediately know what I'm talking about. However, you know, we have to triage and verify if it was patched, if it's workable, if not. So yeah, the solution was OpenCV. And again, we failed. So we started with a RAM disk, and we crashed in the research we were using. This specific cluster was also being used as something else, and
that was actually my bad. I take responsibility for that, because I didn't know that they were using that cluster, and I just did something else on the same machine and rebooted and threw everything away from RAM. So my bad.
And we lost a lot of crashes. Thank you, Guy. I love you. Oh, and yeah, another thing is that these kind of systems are very noisy when it's logging related. We were doing everything logs to be able to actually afterwards try to identify something useful. And these logs were huge. So that huge that they fill our disk. And we'll again, lose some valid crashes, and this time it was my fault, not his. So,
we share the blame.
So, yeah, faithful, because exploitation is hard. DevOps is a very, very complex problem, as we all know. But we eventually got our grip. And when we got our grip, things changed significantly. Our preliminary results, we basically found almost every exploit category that you can imagine. Not only that, when we took a look to the repos, we found that there were a lot of back collisions, which means that we are not the only ones that are playing in this area. A lot of other players in the industry are also doing phasing to these specific frameworks, and a lot of us were having a lot of bugs to report. So huge bug collisions in times of weeks even. And we had huge amount of crashes.
We're talking thousands of crashes to sift through and trying to get what actually something means. Is it important or not? Triage is difficult when you have so many.
And further, have you ever take a kid to a candy store and told him you have unlimited budget and you can buy whatever you want? We were like this. We're playing with whatever we're having, and we're saying, cool, now I have this kind of exploit. I'm going to play this one, I'm going to exploit this, and then we move, but this one is better. No, but this one is better. So it was hard.
Also a lot of fun.
Yes. At the end, again, we had to get our grip, and I'm going to be as honest as possible. We went for the easiest one. At the end, BMP, it's a very easy to craft manually. It's very, very simple file format, and there were interesting crashes in there, and that was what we started to do. So now that I explained what was the entire process, let's try to return to our numbers and objectives. We have IP theft, model tampering, denial of service, DOS misprediction, whatever. Could we approach this kind of different attacks with remote code execution? To be able to do so, we built a lab proof of concept application that would mimic a real scenario where there would be an input, which would be a couple of keys, an image file, and it will produce an output which would give us a label. Simple system, simple common system that probably it's deployed somewhere.
It's actually very similar to many deployed systems that we've seen. We just built it in our lab.
Okay, so demo time. We're going to start with a denial of service. This is a denial of service. On the left side, we're going to have the attacker. On the right side, we're going to see the statistics of the system. So as you can see, everything is normal, everything is running as usual. On the left side, just go and run my, my prediction system. I provide him a bitmap file, which again, a couple of keys. And as you can see, the numbers start to get up and will continue to get up for a long, long, long time, which we don't have. So we are going to do fast forward. And as you can see at this moment, this couple of case file is actually using something like 6.2 gigabytes of memory, and it continues to fill. And it's, again, think about it, 10 Ks, 6.8, and then we have a crash because the memory gets filled. We have an exception, everything crashes. Cool.
Just from a single image, maliciously crafted, around 10 kilobytes. Nothing special about it. Machine is dead.
But nobody likes denial of service. So again, we're going to, on both sides, we're going to have the attacker. So let's take a look. The first thing, take a look at the host name. It's WM. And then we go to the library, just execute exploit. You will probably notice funny stuff on the name of the file. There is an explanation in there, but we're not going to get into details now. Host name, everything's working, and it stays here. And let's take a look at the video where we're connecting now to a shell that was created with this exploit. And I did a typo, and instead of typing host name, I typed host name, and we are now inside the machine. And we can see all the files, and we're a user at this computer, the single image.
So a single image gave us remote code execution on the server running the machine learning system, which is pretty cool.
And I want you just to take a look at this. We are going to return to this directory listing. It's important. I'm not going to explain it now. But still, we are not doing what we wanted to do at the beginning, which was to do model tampering. So we are going now to connect to the machine. We're inside. The machine is running. Okay, so first take a look. This is how it looks, an image file, a label file. We have the number and we have the description of it, okay? Now we're going to run the exploit in a couple of seconds. And we have a segmentation fault. We all know what this segmentation fault actually means. And now we're going to take a look again at this image file. Oh yeah. So now every prediction is going to tell me that it's hacked.
So this is a funny example, but we could have done it to a real system and just modify whatever we wanted to modify. So a hacker would go after tampering that system, and there are no monitoring or metrics in place to say, okay, somebody messed around with the way that the data or the image is constructed, the image file, I mean. So this is just an example, but it shows you that model tampering is a real issue. And we don't have toolings to detect that it happened right now.
Oh, and we're going to do the last demo, the IP theft. Actually, no. You actually saw it before. I don't need to get into details and to run another video to you. You saw that I have the ability to see all the files that exist in the full system, and the same way I did that shell, I could just bring them to me. So basically, game over. I mean, we can do this and easily. So yeah, RC is the king. However, I'm going to tell you about a little problem that sometimes exists. Again, we were lucky. We probably this kind of stuff, it's not going to be with us for many years. Probably it is. I don't know. This kind of bugs exist. But we don't always got remote code execution. So if you don't have remote code execution, you do the most intelligent thing that you can do ever. And it's just go to Guy.
Thank you. Okay, so what Ezra described so far is that if we have a remote code execution on the server, we can do a lot of things which look like they're relatively easy. They're not, but they are very doable. So if you have the knowledge, experience, exploitation techniques, you can go after the server. But actually, there are other methods that you can employ which are much more interesting. In a sense, they don't even require you to know these kinds of exploitation techniques. And I want to describe a couple of them. The first one that I'm referring to here is a cloning, a functional cloning of the machine learning service. And what do I mean by that? Imagine that you have some sort of machine learning service, maybe somewhere up in the cloud. It has a public-facing API, so you can run queries against that API, and you get results from that API. Doesn't matter what kind of machine learning service it is. It might be you upload binaries and get results if it's malicious or not. Might be an image classification. It might be Alexa. Okay, it's a public-facing API with some black box in the backend, which you have no knowledge of. But what you can do actually is use that public-facing API to train your own system using the knowledge already encoded in that black box. And that is called the cloning attack. Using that cloning attack and using that oracle somewhere up in the sky, you can significantly accelerate your training time, and rebuilding the same system or functionally the same system on your end, just using those APIs. And I got a common response that I get when I say this, well, you can just rate limit the APIs. Well, of course you can, but your customers are using the same APIs. What would you do? Well, I'll attach a cost to those APIs. So each API query will cost me $1. Okay, but if you invested $10 million in building that IP, I will invest $10,000 to steal it. So most of the common practices that we have to protect against these kinds of attacks are really irrelevant against the type of attackers that we're trying to defend against. There are a couple of different variants of these kinds of attacks. The first one is what we call a white box cloning attacks. In a white box cloning attack, you have full access to all of the information. You know the topology, you know the functions, you know how the inputs and the outputs behave, and you would say, okay, this is not a realistic scenario, because who would give you all of that information? Well, surprise, a lot of companies who are doing machine learning stuff will go and talk in different academic symposiums. They will present their work in different conferences. They usually hire data scientists, which are usually people with PhD, which means that their own PhD dissertation is probably the reason that are working in a company, and dissertations are public. You just have to drag your feet to the local library and get a copy. So all of that information and most of the articles, PDFs, etc., are freely available, and they will give you a huge amount of information that you can base your cloning on top of. And that means that constructing a white box attack is not as complex as you would imagine. And we've done that. And we've done that successfully, hugely successful. It was such a success that we got somewhere around 1.5% to 2% accuracy loss from our system to the original system. We thought it was going to take us like 300,000 queries, 100,000 queries in magnitude. The reality was that we were able to clone with that accuracy in under 5,000 queries. So this is not a very difficult attack to execute. A gray box attacks is a bit more difficult. A gray box attacks means I don't have access to the PhD dissertation. I have no idea what they're doing inside, but I do have some domain knowledge. And what that means, it means that even if I don't have access to the data set, let's say that you have a machine learning system somewhere who is doing traffic sign recognition. So you know if it's a stop sign or a right-of-way sign or a serpentine sign or whatever. And you build it out of the USA database for traffic signs, whatever. I don't have access to the database. I only have access to the Oracle. But I do have access to the Brazil database of traffic sign recognitions. I can use that database or same domain knowledge from a different data set to do my attack. And it will still work with a very high accuracy. And that means that even you're very protective of the data set that you've built your IP on top of, if I can get similar data set, I can still clone your model. The last type of attack is a black box, where we are actually clueless. We have no idea what this thing is doing. We're not even sure if it's sharing all of the information that it can with us. Sometimes we put filters on the outputs, so you won't give us your top 10 predictions, you give us your top 1 prediction. So we're not sure that we have full access to every aspect of that system. That's a black box attack. So we're still working on those attacks, and we've made a lot of progress, and we feel that they are very doable, and maybe we'll be here next year to explain this. But then again, maybe the attacker has no access to the data. What can he do in that case? Well, another very interesting thing, if the attacker has access to the training data, what can he do in that case? So if you have access to the training data, which might be easier than you think, especially when you're considering supply chain issues, where you get the data from. Data scientists are not very good with data hygiene in general. And I can manipulate the data in order to manipulate your system. And I can do it in a very crude brute force type of thing and corrupt everything, which is nice, but very detectable because nothing will work. Or I can do this very strategically, surgically, manipulating very specific inputs and creating backdoors into the system. So we've been dealing with backdoors for quite some time now in the code sphere, in the software sphere, but in machine learning, it's very different. And the reason it's very different is, again, I remind you, that the result of all of that work is a matrix. The matrix encodes all of the information that you train the system on, but it's not reversible. So even if I get the machine learning model, I bought an appliance from a vendor who runs some sort of AI appliance, and I'm looking at it, and I have full access to the appliance, and I can do whatever I want with the appliance. And I run all of my validation tests, meaning I get positive cases, it works. I give it negative cases, it works. The system is working brilliantly. I have no way to know if there's a backdoor built into the system because I don't know the password, I don't know the magic number, I don't know the magic header. And without it, I have no way to discern what it is when I'm looking at the matrix. It's not reversible. And that is a huge problem. And it's a huge problem both in academia and a huge problem in trust, in the way that we are trusting AI systems right now. Because when I go and buy something from a vendor and introducing it into my own network, I want to trust that appliance. I want to know that nobody injected a backdoor into the system, so I will be absolutely certain nobody has access to my system when I'm plugging it into my architecture. But if I have no verifiable way to test this, to know this, what would I do? What can I do? And by the way, the answer to that question right now is nothing. We don't have tools. We don't have ways to navigate these problems. In the end, all of that information is encoded into that matrix, into that machine learning model. And the way that that machine learning model reacts to the inputs, good inputs, bad inputs, backdoor inputs, whatever it is, determines the behavior of the system. But we can use that to do other things as well. So I want to show here from this year's Black Hat, like a month and a half ago, work from IBM called DeepLocker. And what they've done here, which is very interesting in my opinion, is that they've built a machine learning payload password generator of sorts, which means you have a malware, it has an encrypted payload, and it will only become active or be triggered if a specific set of parameters are set. It shows that there's a specific key in registry and a specific file in the file system, or whatever you want to trigger it on top of. And if you don't see these triggers, then you will not behave maliciously. Usually what malware researchers do, they look at the file, they look at the binary, they disassemble it, and they analyze what the triggers are in order to understand what triggers that behavior. But now they encoded all of that information into a machine learning model. So they have a piece of malware which behaves completely naively, nothing very important, unless it sees the right triggers, and only then it becomes malicious. But the reverse engineer, the malware researcher here, has no tools, has no way to look at the matrix and determine what the triggers are. We have no way to decipher what that means. And it means that if somebody in the malware field will actually build such a real world malware, we would not have a way to look at the binary and understand what caused it to behave the way it does. We will know it did whatever it did because it did some ransomware or it caused some damage, but we'll have to investigate the entire system and not just the binary and do lots of experiments to see maybe this triggered it, no, maybe that, maybe the combination triggered it. It's a very difficult problem. Another thing is misprediction. I mentioned in the beginning of the talk that the systems are optimized to look at the strongest signal that they can find in the input. And we can take advantage of the way that the systems are constructed by creating our own strongest signal in the input. And there was a lot of let's say, discussion or argument or lots of shouting in the academia and the real world. Does this even apply? Because it's very easy to show that it applies to two-dimensional images, stickers, stuff like that. But in the real world, we have camera angles and we have zoom issues and we have lighting problems and objects are 3D, they're not 2D. So would that even work in the real world? And the short answer to that is yes, it does. So what you see here, it's not an actual turtle. This is a 3D printed turtle. And you will look closely at the top shell, you will see like red spots or red dots. These are the maliciously crafted strongest signal to that image. And if you will look at the bars on the left, you will see that whenever the top shell is topmost, it is identified by the system as a rifle. The system here is Google's Inception v3 object recognition system. And what they've constructed here, or what they've shown here, is that they can apply this adversarial image or adversarial construction to a real world 3D object that will actually cause the system to mispredict or misclassify that object as whatever they decided it would be. In this case, they decided that this is going to be a rifle. So, excellent work. I want to show you a different way to do these kinds of attacks. And for this, I would need you to listen closely.
Without the data set, the article is useless.
So this is the original sample, the original audio sample, as you would probably hear it. And this is the adversarial sample, or the malicious sample.
Without the data set, the article is useless.
Show of hands, how many of you heard the hacker? Payload, something abnormal. I'll play it again. One person.
Without the data set, the article is useless.
So what actually happens here is they multiplex a second audio stream on top of that one, but they modulate it in such a way that it's a much stronger signal than the person that is speaking. And what the system would hear is, okay, Google, browse to evil.com. That is the machine learning focusing on the strongest input in that system. And that means that even we are thinking that we are hearing it in a commercial on TV, okay? We think that we hear it and we think we know what we're hearing. The system might be hearing something else completely. And that reminds me of a different story, that even if there is no malicious attacker, these systems are acting pretty funny anyway. So there was a story like maybe 12, 14 months ago, a little over a year ago, that a woman was interviewed on television, the local television news in America, and she was talking about her Alexa and how much she's very fond of her Alexa, and she wanted to give an example, and she said, Alexa, add toilet paper to my shopping cart. And lo and behold, Alexa added toilet paper to the shopping cart. But then they aired that interview, and 20,000 households had Alexa adding toilet paper to their shopping carts. So that was not a maliciously intended attack, but then Domino's Pizza decided this would be actually an excellent idea and air such a commercial during the Super Bowl, where everybody would, Alexa, order me a pizza from Domino's. Not a good idea. Somebody blocked them from doing that, but there was a lot of controversy. Can they or should they be allowed to do that or not? Yeah. Okay, another very interesting work. This is from 2 years ago, from DEF CON 25. And what the person built here, he built a machine learning system that uses VirusTotal as an oracle. Who's familiar with VirusTotal here? Okay, about half of them. So, okay. High-level description, VirusTotal is a service that you can upload binaries. It will run them against a couple of different AV systems, and it will report back a score, meaning how much of a malicious prediction is this binary. Is it very malicious, not so much malicious, etc. And what he built was a machine learning model that trained in order to recompile the code, to change the code, mutate his code again and again and again and again in different paths, and using that oracle to lower the score that he was getting. In the end, he got a 0.49 score, which means that his virus was no longer treated as malicious. Everything that he had to do in the end was remove the .text section, rename it to something else, and copy-paste the notepad exe .text section to his own virus. So that was the best method in order to circumvent all of the different best antiviruses systems that we have in the world today. So, privacy. Machine learning is leaking privacy all over the place. So, a lot of people are not really aware of that or discussing that, but that is the reality of the situation. And I'll give a very short example. So, imagine that you have some supplier building a diabetes detection system. So, he contacted some people, some of them have diabetes, some of them do not, and he trained his machine learning system to detect diabetes based off blood samples or whatever. And he sold it. Now there's an appliance somewhere in the world being sold to an insurance company so they can run it against their own people applying for an insurance policy, and they can decide to give them a health insurance or not. So Joe comes along, and the machine learning system detects that he has a 7.4% chance of being diabetic. Or maybe he has a 35.3% chance of being diabetic. I don't know, the system is working. Very happy. But then Philip comes along, and Philip was part of the original data set the system was trained on. And because of that, we are going to see much higher numbers. We are going to see 96.2% probability, which tells me with almost absolute certainty that this person was part of the original dataset. I just leaked his PII, his private identifiable information, because that's the way those machine learning systems are constructed. Takeaways. What we want you to go away from this talk with are 3 different types of takeaways. If you're researchers, think about your trust model. Think about the way that you are building those systems. Think about the emphasis that you need to put. think about the emphasis that you need to put on the infrastructure and the interfaces with the different components in that infrastructure, because here lie dragons. Someone needs to look at this. If you're an attacker, wow, nifty. There's lots of exciting stuff you can do here. Nobody's really doing this. It's a ripe field. Go ahead, do awesome stuff. That's my best advice to you. And if you're a defender, you really need to think about how you're going to sanitize the data coming into the system. That's the biggest attack vector that you have today. You have a public-facing API, you can't just put it publicly. You need to do something to make sure that you're getting the right information into your systems. You need to validate the data, and you need to think of your data as untrusted. It doesn't matter if you're using TLS. If I, as an attacker, am using that TLS connection, it doesn't matter if it comes all the way to your server as encrypted and protected from everybody else. I am the attacker. It doesn't matter if you have TLS. Think about those issues. Think about everything that we've discussed. And most important, stop being scared from AI. AI might sound very, very scared from a mathematical point of view. In the end, it's just someone else's code. We want to acknowledge the various people on our team who actually helped out tremendously in constructing those attacks and this talk. Omer, Adi, Dennis, Rezi, Adel, Sapir, and Oleg. Some references, again, you don't really need to take photos of it. And in the end, we challenge you, we ask you, we recommend that you come talk to us, learn more about this subject. We believe it's important. We believe there's a lot of future in understanding machine learning and AI. Questions?